Okay, so we are starting on superposition, question 10. Right, so question 10, right? Okay, before question 10, all we needed to do for the double slit experiment is you identify that it's a double slit experiment, and then you apply y equals to lambda d over d, right? So that's the equation for double slit. So quite easy to solve those questions. So there's another type of question that A level was set, and it's something that you all need to understand as well. Basically, instead of just applying the equation to solve the problem, right? What we will need to do is...
Oh no.
Oh no.
Oh no.
Yeah, it's fixed. Hey, hi guys. Welcome to join. Then I need to record. Okay, so I record. I got Ethan not here. And Jolene is definitely still busy. Oh, she's gone. Sad. GG my voice. Go ahead. Okay, so the other type of questions, right, is like something like question 10. Like if you look at the question 10, right, you apply double slit equation, right, you also know use because the wave from the source is changing, correct? So the pattern that you get is changing. Like they're asking you to increase the frequency and see what changes you observe. So in this case, you go back to first principles. Why do we even get changes in intensity of a receiving point in the first place? What effect causes this? What effect causes a change in a point receiving waves? A change in the displacement of the particle at the point, maybe? The name of the phenomenon? Interference, right? Yeah. So we got interference. So interference is basically when two waves meet at a point, the sum of the individual wave displacement gives you the final wave displacement at that point, right? So at the point here, point P, there is interference because from S1, right, a wave comes here. And then let's call this distance x1. And x2, there's a wave coming here. And this wave is x2. So to check how the interference affects our point P, all we need to do is sum the two waves coming there. So we know that if two crests happen to meet here, you get a double crest, double the height of the crest. If two troughs, you get double the depth of a trough, right? So basically it's about whether the two waves meet and how they meet. So now that we know that they meet at P, the next question is, what is the phase difference of the two waves after meeting at P? And that can tell you whether the amplitude will be double the amplitude or 0 or somewhere in between. Right? If it's constructive interference, you get double the amplitude. If it's destructive, you will get 0. If it's in between, you will be some number in between. Right? So we need to find the phase difference. So what determines the phase difference at P? Pardon? How many wavelengths can fit the distance between them, right? So actually that difference, so assuming these two are the same line, then this is the extra distance, right? This is called the path difference. So it's determined in part by what we call the path difference. And there's one more factor as well. Right, but two factors that determine whether you meet in phase or out of phase or not in phase.
Is it frequency?
We have looked at the two already after the run. Pardon?
Whether the source are in phase.
Yeah, whether the two starting point, right, they're in phase or not. Okay, for example, if there's a phase difference between S1 and S2, even if you can take a nice number of waves here, they still will not be in phase because they started at different times in the first place. So like this guy crashed halfway already, then this guy will crash up, then out. You won't necessarily get a nice pattern, right? So the other factor, right, is to check the source phase difference. So these are the two factors to check. In this question, they already make things easy for us. There's 0 phase difference in this question. So it's easy for us, right? All we need to do is just check the path difference. So even without doing the question, we can check the criteria for the two waves. If I can fit an integer number of wavelengths inside this extra length, right? And this extra length is just delta x, x2 minus x1, then I know I will be able to get constructive interference. So for constructive interference, the path difference must be n lambda. Right? Then for destructive interference, I want a crest to be a trough. So I must fit in 1.5 wavelengths here, half a wavelength here, 2.5 wavelengths, 3.5 wavelengths, and so on and so forth. As long as an extra half here, crest from S1 will meet trough from S2 and vice versa. Right? Then they always tend to cancel each other out. So constructive interference, the path difference needs to be able to fit in n plus half wavelengths inside it, where n can be 0, 1, 2, 3, 4, 5, integer numbers. Right? So you all agree that these are the two conditions to get constructive and destructive interference, right? So in this question, right, they actually do give us the dimensions of all the lengths. So this one is 5, 4, 3. Is a nice ratio for length, right? So if they give us this distance, we can straight away find delta x, right? Delta x is 5 minus 3, 2.0 cm. Okay? And we're supposed to find wavelength, but they didn't give us wavelength, right? What did they give us instead? They gave us the speed of the wave and the frequency of the wave. So we can use v equals to f lambda, make lambda the subject, so it's v divided by f, and the velocity in this case is 10 cm per second, and the frequency is 5 hertz. So it's 10 over 5, this gives me 2 cm wavelength. So we can check for the basic situation for A. We have constructive interference, right? Because from A, right, we see that, hey, the path difference is 2 cm, but the wavelength also 2 cm. So we'll be able to fit exactly one extra wave in this extra length, one extra wavelength. Which means the crest that comes out of S1 will meet the previous cycle crest that has come out of S2 because it is one cycle behind, right? Because it has to travel one extra wavelength. Right? So the crest will still meet crest, and S1 and S2 are in phase. So our two criteria in phase and path difference is actually a multiple of the wavelength, which means that we will have constructive interference. If you have constructive interference, our interference, the idea of interference is we will just sum up their amplitudes. So the resultant amplitude is the individual amplitude, so it's 2A. So it is possible in this question, right, that the answer is not more than 2A. For example, if I make one of the source stronger, like it emits amplitude 2A, this one emits amplitude A, then when I have constructive interference, it can be 3A total. You just need to add up the individual amplitudes of the waves. And that's basically what the principle of interference states. So if you need to explain why these things happen, right, you will explain from interference first. Then you're going to explain that the waves need to be in phase or not. Then you describe the two factors. Then finally, you will say given this, for phase difference, for path difference, if it's n lambda, you get constructive interference. And vice versa, n plus half lambda, you will get destructive interference. Okay, you all managed to work this. Are you able to work this out now? Come take a look. Are you able to work this out now? Okay, if you didn't get it, and now you get it, you can go try B and C if you were not able to. Then we cover it. Alright, we're going to do that. So you know to do A now. Okay, great. Yeah, hey, how do you do that calculation? Give the formula and then and the. So for B and C, right, if you already got the answer for the first one is 7.5 Hz. Okay, if you already got the answer, right, why don't you come up with a general equation to find the first three values of frequency? Okay, and then after that, I want you to also tell me why the n equal to 0 doesn't work. So actually, n must be equal to 1 in each of these cases. So you must be able to explain why n equal to 0 doesn't work. Is there you can do B and C? Couldn't do, huh? So now can try. The criteria here is constructive interference must be n lambda, destructive interference must be n plus half lambda. So since there's wavelength here, but the question talks about frequency, you're going to need to be able to change frequency to wavelength. Or wavelength back to frequency, either or. Either you change this to frequency, or you change frequency to wavelength and put in here. So that's your challenge. Are we after you done? You want to do B on the board? I'll do it with you. When I ask, actually it wasn't a question. Which one? Is that?
So you increase the frequency is the V of
because the medium doesn't change.
oh.
Guys, if you're unsure whether V or lambda changes, V doesn't change because the medium is the same medium. Right? Yeah. In fact, this is light. So if you're traveling through air, the speed of light is the speed of light still. Right? It's a laser, right? So the speed of light is 3 times the power 8. Wait, sorry, this is not a laser. That's the next question. This one, the speed is 10 cm per second, I'm sorry. Salah. But the speed doesn't change because the medium is still the same medium. That means they're not changing the depth of the water. It's water, right? Yeah, wave generator producing water waves. Is that how? You got it? Yeah. Where's the answer? So can you get a few more values? Oh, so okay, you got 75 is the first time you get it, right? I want to know the general equation for all the subsequent values of frequency. This one, n plus half of the half. Yes, so now go substitute n equals to a few values so you can see what frequency you get. I think plus 2.5, right? Not plus 25. Yeah, because you expand the 10 by the time you go into the half. Yeah. Think about the half became 5. Yeah.
You submit different values of n.
Because n is an integer, that means they're basically saying how many you can sub in, right? So that's the frequency that will produce that value. Because they're increasing the frequency. But that also makes more sense. When you increase the frequency, right? You're actually being able to fit more waves inside. Right? So that makes sense. You should be able to fit more waves inside.
So the equation will be 2 equals to n plus half bracket n over.
Yeah, something like that. So just do that.
So submit appropriate values
To get what?
the submit appropriate
Values of n to get, and then check what frequency those correspond to. So each value of n has one frequency, right? So you want to try, Abi? Let's go. Yeah, of course. No need, okay, thank you. N has to be an integer, yeah. Because we decided, we agreed just now, right? For constructive, you have to have exactly a certain number of 4 wavelengths inside. For constructive, you have the whole number. For destructive, you have the whole number plus exactly half. So that's why my n is the integer value. Right? So for both of these, n is is it integer symbol? Yeah. Yeah, I'll check. My math bit does be really, but yeah. Abi, let's try. Do it together or not? So you start with destructive interference. What's the criteria? Because for part B, they want destructive. Okay, you can write that off. You start this first. Oh yeah, you can start that with 2, no problem. Then I only F the subject, right? Because F is what you want to define.
Oh.
Okay, then let's expand for n equals to 1 to. Okay, so give me a few iterations of n.
It's 1, F is 0.5, F is 1. But we want to work on that.
Yeah, that's why you don't quite use.
It's not for them.
Maybe it was. But equal then just like something common. Equal. Or you mean just do mental sums lah.
Okay, we can do that.
Yeah, it's okay. That's not what it is, right? N equals to 1.
3 is 1.
7.
7.5.
Oh, start at 1. Start from small.
Oh, okay.
Okay, you write everything in one line. Right. A, comma, B, comma, C, comma, yeah. Okay.
Wait, so, what do you want?
This one is on D, okay? D like first one.
Oh.
Because they say increase on 7 from 5 onwards, right? So did it correctly, we started off with the criteria I want distributing difference. They say distributing difference colon. The path difference must be n plus half lambda. But since I want frequency, right, I can substitute lambda as d over f, and then make f the subject. So you get this general equation for the frequency, and each of these corresponds to fitting in 1.5 wavelengths or 2.5 wavelengths, so on and so forth. And that depends on what n is, right? So once you expand, you can sub in a few values of n to try. So you realize that the series is 7.5, 12.5, 17.5, so on and so forth. I just keep plus 5. These are all the frequencies that will give you disruptive interference at point T. Right? Because what we're doing is we're increasing the frequency more and more and more and more. So we're actually being able to fit more and more waves within this small area. Right? Then of course they say I start at 5. So the first time I can get it is 7.5. So if you start n equals to 0, right? If you start n equals to 0, you will get only 2.5. 2.5 will give you disruptive interference, but there is no 2.5 in the question. You start at 5. So therefore, this is the correct answer.
So they can be
Make sense? Okay.
when the whole wave is not being maybe like
Because.
Let's see.
That's why is it the same? Just minus one.
No, that's what?
Figure it out.
Yes, take away the half. So let's leave it out.
Now I copy my friend's work.
Minus 5, but you graduate.
5n. Bring the f to the left hand side. Bring the 2 to the right hand side. 10 divided by 2. N is the numerator. Then ready, right? Yeah. So which one I choose to be the answer? Yep, that's be 10, right? Cannot be 5, right? Why cannot be 5? Start with 5, and the question says the next one. Yeah. Okay, so you see a pattern. Once you get these general equations, I write a few out to show the examiner you know what the pattern is. Then you choose the correct answer from there and write a statement to say that you want to do this because it starts at 5. So the next one is 7.5.
So why can't you?
Because it starts at 5. So the question says what is the next one, not what is the first one, not what is, yeah, they say what is the next time it reaches maximum. So you'll see that what you're doing here is first principles. You're just checking whether the waves meet in place or not, right? Rather than applying a double state equation, because your sources are changing in this question. So it doesn't make sense to apply double slit equation. Double slit equation is that you have many points along the line and you want to check some pattern dimensions like, oh, you know what's the distance between points, or what's the angle of one point to another, or what's the width of the pattern on the screen, that kind. Then you use the double slit equation. If you're looking about just one point, two source, you use first principles. Check how they meet. Okay, quick question. What if the sources are out of phase?
Then you have to
Minus from the.
How does that change?
you have to find the point angle.
Oh, di then it's di becomes the CI equation.
Yeah, it just swaps. If they're out of phase, it means when a crest comes out here, a trough comes out here, and they meet. If I can fit an exact number of wavelengths inside. So if I can fit an exact number of wavelengths inside, a crest will end up meeting a trough, right? All the time. So this one will become the destructive interference criteria. And this one will become the constructive interference criteria. Yep.
But that's only the anti-phase, right? Then what if they're like
What they're
already
phase
out?
difference away, then the destructive interference and the constructive interference will require you to modify this to become the phase difference. So you need to check.
Yeah.
Right? So let's say they are 1/4 cycle away. Then the constructive interference will be, I need to fit exactly 1¼ wavelength. So you know how to modify that?
N plus 1/4.
Yeah.
Okay.
So that's how your pattern is.
Wait, then I have to add 1/4 again to the second one.
Then after that, you need to add half to the second one.
Huh?
For disruptive, you need to add n plus 1/4 plus half. So it will be n plus 3/4 wavelength. Right? That makes sense, right? So technically, you could do this for anything. Usually A level, they won't make it too complicated by giving you a stupid number of phase difference like 0.7 radians or something like that. Usually they give you a nice round number. 99% of the time, they just ask you for constructive or disruptive because otherwise it's very hard for you to explain what you're doing. Right? Okay. But you all get the general idea, right? Okay. So just remember two criteria for phase difference. Okay, there's two criteria. Most of the time, you just test one or the other, not both. But they could like ask you a thinking question. You know, what if the sources are out of phase? Okay. Right? Okay. Good job. Okay, so I think this is the last double slit question. Right? 11 is not earlier. Or is it still more double slit? Yeah, okay, we are done with double slit. Okay, how many recap now? So we're not doing double slit anymore, we're doing diffraction grating. What's the characteristic equation for diffraction grating?
B sine theta equals n number.
D sine theta. Now what's the D in the D sine theta?
The smaller way.
Isn't this more different?
Yeah, it's the one on the slit.
Oh, difference between states.
Yeah, distance between slits. So this one the units is in meters or length lah. Okay, so let's look at this question. We got red light. Okay, 469 times 10 to the 14 hertz incident on the diffraction grating, and it does the 3000 lines in 1 cm. Basically, in 1 cm, there's 3000 lines. So 3000 slits. Right, now the question is, apply the equation to determine the maximum possible number of intensity maxima on the screen. So I have my slit here. Light comes in, light will come out, right? And it will fall on the screen. This angle is theta, and this is the 0th order, and this is the nth order, and that's how we apply our equation, right? What's the maximum value the angle and the theta can take?
90.
90, right? If my angle theta is 90 degrees, I will technically require an infinite long screen, and it will be infinite distance away, technically lah. Agreed? But that's the maximum I can go. So actually, I can just use inequalities to be say less than, theta is less than 90 degrees. Okay, what happens if theta is more than 90 degrees? Where will it end up? If you're on the other side, right? Then that one won't use the diffraction grating formula because technically you didn't pass through the diffraction grating, so some kind of reflection. Okay, there is still an effect, but that means you are sent here at an angle to get the reflection. Okay, so not covered within the scope of our learning, right? We only get diffraction of the right hand side. So, in this question, sine theta we can say d sine theta max equals to n max lambda. So we can find the maximum value of n. Right? If we strictly less than, we have to use sine 90 and theta max must be less than 90 degrees. Right? I can't get 90 degrees. 90 degrees I mean an infinitely long screen. So, sine 90, what's the value? 1. So basically, this is just d over lambda. But I don't have d and I don't have lambda, so I'm going to need to work it out, right? So let's find d. D is 1 over lines per meter. So 1 over 3000. But that one is per cm. So I can per 10 to the minus 2 here. Right, so if you did this calculation correctly, it should be 1/3, right? 1/3 is 0.33333. Huh? Yeah, 3.33333.
It doesn't refer to the distance between the screen and the
No, it doesn't. In the direction grading, d refers to the distance between slits in the slit, in the grating itself. So usually a tiny number. Okay, so 3.333, let's work out. Please 10 to the minus 1, 2, 3, 4, 5. Then I bring 1, so 10 to the minus 6. So this is 3.333 micrometers. Roughly 8 micrometers. Okay, the math you all can work out, right? Not easily confused. Okay, if you're confused, change 300 lines per cm into 300 lines per meter first, then you do your calculation. Okay, now let's find the wavelength of light. The wavelength of light is going to be v equals to f lambda. So lambda is v over f. This is a red laser, so the speed of light. Frequency given to us is 4.69 times 10 to the 14. So we get 6.4 times 10 to the minus 7 meters, which is also 640 nanometers, which is still in the red light color, red light part of the visible light spectrum. Right, so now we can do some calculation here. N max must be less than 3.33333 micrometers over 640 nanometers. So it must be less than 5.2. Right, and n is an integer value. Right, n is an integer value. So therefore n max must be equal to 5. So this means I can see 5 orders beyond the central maximum. The central maximum starts from 0. Because when I substitute n equals to 0, I get theta equals to 0, it goes straight line through, right? So how many maximas, the total number of maximas? Did you know how to find the number of maximas? Is 5? Times 2? But this is 1, 2, 3, 4, 5, right? Yeah, plus 1. Plus. See? 0. I got 1, 2, 3, 4, 5. Then on top I got 1, 2, 3, 4, 5. So that 10 on top and below, right? Then plus the central one, that should be 11. So the formula is 2n plus 1. Okay, so not minus 1. So sometimes, just draw how it's easier to draw. You can count at 11 here. So they want us to find the length x, where x is the distance between the 0th order and the 5th order fringe. Right? So if you draw a triangle, we see the geometry. This is tangent theta, right? Okay, do you think the angle theta is small? No, right? Because we were just now considering the length of the screen to be close to infinity. So this is slightly less, so it's actually a large number. So we don't expect that theta is small, so we cannot drop the tangent in tangent theta. We must keep it to be tangent theta equals to x over d, right? So from this equation, I can actually find sine theta. So this is equation number 1. From the general equation, d sine theta equals to n lambda. This is equation number 2. Sorry, let me make it a bit more convenient for us. I'm going to say sine theta equals to 5d lambda over d. Right? So this is equation number 2. I need to solve a sine and tangent simultaneous equation, so I can't. So I'm just going to inverse sine and do it. So d equals to x equals to d tangent theta equals to d tangent sine inverse 5 lambda over d. So if we do the substitution of lambda over d that we calculated earlier on, 640 nanometers and 3.33 micrometers, okay, and you sub the value of d given, which is 2.3 meters, okay, then you should be able to get this value of about 7.83 meters. So you see that actually x is actually even larger than d. Okay, so in the diffraction grating equation, we are not using small angle approximation. That was the double slit equation. In the diffraction grating, there's no small angle approximation. This is valid for the entire length. Okay, it also means that the distance between the fringes, would they be equidistant? Not necessarily, right? Won't be. In fact, the distance should keep increasing. Sorry? Yes.
So why don't you just find theta first using the diffraction grating formula?
Yeah, now.
But then you did simultaneous.
Yeah, but if you want, it's just 2 steps thing. So I need to plug this value to sine inverse of it, then tangent it, then find d. Still need to, it's still the same thing, right? Yeah, I just combine all the calculations into one step. It's the same, it's the same. It's not simultaneous equation, we're just solving for x. Okay, all good? See how? Green light. What's the difference between green light and red light? In the next part, they say change to green light. So what's the difference between green light and red light? What quantity changes for light? Frequency and? Okay. So our equation for diffraction grating right there frequency by the wavelength. So let's use the wavelength. Does wavelength increase or decrease when I go from red to green? Decrease. Because red is 700, blue is 400. So to go from red to green, you decrease. Okay? We write this in words. Therefore, for a given value of n, right, theta should decrease, right? Because if the wavelength goes down, everything else remains the same. This is my diffraction grating physical property. So this is unchanged. So if I give, say, n equals to 1 for red and green, the green one will have a smaller angle. So the consequence of this is, number 1, maximas are closer together. Number 2, there should be more maximas.
because how do you get the first point? The maximum of superposition.
Because now the n equals to 1 angle is smaller, n equals to 2 angle is smaller, which means that the distance between 1 and 2 is smaller. If n equals to 3 is also smaller, then the 2 and 3 is smaller too. So all because given the same distance, actually will fit more, that means the distance between them must be smaller, right? Does that make sense? Right? So these are the two. There's actually one more difference. Can I think of it? There's one more difference. Richard, do you know what's the one more difference?
I only put the second one, I didn't get the first one.
Okay, now that you know the first and second one, there's one more difference.
Only put the second one, but not the first one.
I don't know.
Actually, the first one implies the second one, and the second one implies the first one. They are necessarily true, right? Yeah. If you can fit more, they must be closer together because the same distance you can fit more, right? Or if you have more, then by the same, since you have more within the same line, you technically need to be closer to one another. So they are necessarily true. Like, I think depends on the marks in the exam. But there's actually one more change.
Which equation would you use to derive the first equation? The first statement. Like there's the sine theta one, is it?
So this is the only change thing I'm using.
This is the angle.
The angle is covered. The angle leads to these two. Guys, the most obvious thing, red light change to green light, so the red dots become green dots.
What? Then the class goes.
That's a prank, bro.
Yeah, you cannot write that because that's not important. Right? Say how? Red light change to green light, so obviously the dots will now be green, right? Okay. Yeah.
So you almost bring all one.
I successfully did.
Wait, so would you get a mark if you wrote that?
No, you wouldn't get the mark if you wrote that. Although it's not a wrong answer, it is not a relevant answer. Right? Technically it's correct, right? Because the pattern will now be green. Right? Because a green light is used instead of a red light. Okay. So this is the explanation about, and then these are the observations.
It's also there's only two.
Yeah. Okay, part B is a bit difficult to understand. Okay? Basically the question says, why is it better to use a diffraction grating than a double slit to determine the wavelength of a laser? Now, in a diffraction grating, right, we have d sine theta equals to n lambda. In a Young double slit experiment, we have y equals to n lambda d, y equals to n lambda d over d. Okay? And the hint here, right, is what was the requirement to use the double slit equation? Theta must be small, right? So the picture or the image that's produced must necessarily be small. That means basically I can, even if my image is very, very big, I get many maximas and minimas, right? I can only use the small range in the middle because that's when the equation is valid. And I'm going to use the equation to go and find the wavelength. I cannot say, oh, I want to use the n that is very, very far away because the n actually wouldn't be valid. It's only valid for small angles. Right? So, for diffraction grating, there isn't that requirement. That's why we discussed that earlier. See, there's no requirement for the angle to be small. So, it turns out, for experiments wise, right, a grating is much better, right? Because I can say, oh, instead of measuring from here to here, where my percentage error is large, right? I can measure from here to here with a meter ruler. And then the percentage error is much smaller. So, the first thing you can write is, since the diffraction grating equation does not require us to use a small angles approximation, we can use large values of distances along the screen in order to determine the wavelength. So the percentage error of the measurement of length will now be smaller. Okay, I will put that in point form now. Okay, later I'll try to find a video that shows you, right, what double slit experiment the actual image looks like. But you should be able to guess from the previous graphs that you have looked at. The double slit experiment, the bright fringes are really fringes. That means it's bright, but it doesn't become dark immediately after the maxima. The brightness decreases out, so it feathers itself out. Right? So it's actually hard to determine where the central maximum point is for measurement. Okay? And for the diffraction grating, because it is only one point that is bright and every other point is dark, okay, it's very easy to do that measurement. So that's the second reason. So you can say that the maxima in the double slit experiment is more spread out, so leading to greater uncertainty in your measurements. Right? It makes sense, right? If it's spread out, I can't determine exactly where the brightest part is. Right? Whereas if it's just a point source, which is what the image diffraction grating is, then you will be able to get it. Sorry? Because I have a random error in determining where to measure from. Right? Does that make sense? Okay, let me give you an example. Let's say I do an experiment, right, where there's oscillation and there's a ruler that I use to measure the oscillation height. If I use a needle, right, it's easy to determine where the point is. But if I use a fat needle, right, I have to guess where the center of the needle is, and that gives me uncertainty, right? So the same thing is true here for the maxima. If the maxima is spread out, right, I'm like, shit, which part of the maxima do I use? And by right, you use the center, but then I have to do a measurement again to find where the center is. Whereas for the diffraction grating experiment, right, it's exact position because it's just a dot only. So this one is easier to determine where the maxima is compared to this one. So there's less random errors. So the maxima in the double slit experiment is more spread out. It will lead to greater uncertainty in the measurement. More random error in determining where the center is. Okay, later I'll show you a picture, right? You all will understand this super easily. Okay, I'm sure the lecturer has shown you before the image as well. Sababi, go ahead. Okay, so we're almost done. The last two questions is about single slit experiment. Okay, and Rayleigh's criterion. So let's do a quick recap. Okay, so a single slit will still produce an interference pattern of bright and dark fringes, but this will be much more spread out than the double slit one, right? And we know that for the double slit experiment, the single slit one bounds the double slit. So this is the equation that we use for single slit. Sin theta equals to lambda over A, but this lambda is for bright to dark, not bright to bright. It's a special case, right? And lambda is the wavelength and A is the size of your single slit. Okay, but do you realize that we all have this problem? We all see this pattern everywhere we go. You know why? Everywhere we go, there's this thing. It's not just when you see the single slit here. Does no one realize you have it all the time? Your eye is a single slit. So technically, when you're looking at sufficiently small items, that they blur out.
Does that mean like when you blur out things in your eyes, it's like the image is not well resolved?
Yes, right. So this is how we explain Rayleigh's criterion. So Rayleigh's criterion is also sin theta minimum is equal to lambda over A. It's the same equation, right? But in this case, right, we're using a special consideration. This is basically, if I have a single slit, right? If I have an object here, he will produce its own pattern, right? Because of the single slit. If I have a second object here, he will produce its own pattern. Now, if these two objects, right, are sufficiently far apart, right, no problem, right, the pattern will be sufficiently far apart that even if they are slightly blurred, I can still tell that they're two objects. But can you imagine, right, if these two objects get closer and closer and closer together, these two patterns of mergers will get closer and closer together, then I can't actually tell when one object ends and another begins. Okay, let me give you a very real example. You know what I'm talking about already. Okay, how many of you have gone to countryside before? Anybody never go to countryside before? Over there in Singapore. Okay, never mind, then use a bit of your imagination. You watch TV, you'll be able to see. Okay, so you know the scene, right, where it's dark, but there's a mountain road. Everywhere is dark. An object that is from very far away, right, will look like one dot. One bright light. Then as it comes closer and closer and closer, it will split into two lights. What are you looking at?
The headlights of the car.
Yeah, headlights of a car, because the car has headlights on left and right. So when they're far away, right, you can't make out that it's two headlights. It will look like it's one headlight. And the same thing is true of like stars that are very close in the sky together. So sometimes the stars actually really is two stars. But you look with your eye, it's just one star. Right? Then even with some small telescope, okay, you are actually changing the size of the single slit. Technically, it still looks like one star, unless the scope is big enough. So there's double stars in the sky. There are binary stars that we studied before in gravitation that can be resolved with the correct size of telescope. Like maybe you use binoculars, it still looks like one star, but with a sufficiently large telescope, because you increase the value of A, the allowed minimum distance changes, then you get to resolve them. It's called resolution. So this is Rayleigh's five theorems about how far away objects require to be from each other in order for you to tell that they are two objects. So for this first question, right, it's quite easy. The context of this is just the same thing here. Okay, the criterion basically says that how far apart must the two images be for me to be able to tell that it's two? The requirement is when the maximum of one of the pattern is at the minimum of the other pattern. So basically, it is still this requirement because the bright to the dark part. See, this is the bright to the dark part. So we just take one of the patterns and find the bright to the dark distance. That's where the other pattern's bright part must be. So we're actually matching these two together, and we're saying that hey, this angle for one of the pattern must be also this angle that separates the two objects. Right? You see that there's an angle that separates the two objects. This is called angular separation. So let me give you an example. I look at the back of the class. Right, there's a whiteboard there. The whiteboard from left to right has an angular separation. How do I tell what the angular separation is? We can do a quick measurement. This is 180 degrees. So this is about 90 degrees. So let me rotate. Okay, too much. I halve it. Okay, the whiteboard is about 45 degrees angular separation from me, the two ends of the whiteboard. Okay, so this is what angular separation represents. Which means, of course, depending on the distance, I can get larger or smaller objects with same angular width. Like if the whiteboard was further away and bigger, it could give me the same angular separation as a whiteboard that's smaller and nearer to me. So you're more likely to be resolved under Rayleigh's criterion if number one, you are nearer. Number two, you are further apart in reality. Right? So that makes sense. So let's look at question number 12, the context. The context is I have a satellite that got two solar panels. This is something like the International Space Station. There's many solar panels on it. And you're going to look through like a binoculars, right, and tell that there are two different solar panels. Basically see the solar panels on the ISS instead of seeing it at the top of light. Okay? How good must your telescope be? Okay? So it turns out they're using an 85-inch telescope. Sorry, not 85-inch, 85mm telescope, which is roughly this size. Okay, I have a telescope at home that's 85mm. It's called a baby cube. Right? And then, I want to check, what is the angular separation? So let's find angular separation.
So the largest separation of 120 angles.
Yeah. So, I'm going to find an angular separation from the physical dimensions in space. The question tells us that this satellite is about a distance r from us, and the distance between the solar panels is a certain distance. So the distance between the solar panels is 24 meters. Still got time, right? Yeah. 24 meters, right? So actually, by right, I'm using S equals to R theta, but I'm going to cheat by saying that the arc length is the same as the horizontal length. That's because if the R is sufficiently large enough, right, the angle of the arc is almost the same as the angle of the chord. So, theta is S over R, approximately. Right? And the S is 24 meters, and the R is, given in the question, is 330,000 meters. So you can see that the distance is really very large compared to the arc length. So actually it's a very tiny little angle only. And if you calculate this, you get 7.3 times 10 to the power minus 5. Jen, what's the units of this? Radian. Must be in radian. Okay, you know why? I'm using S equals to R theta. You remember in secondary school this equation can only use radian because radian is a ratio. Right, to calculate radians using a ratio for circles. Okay, so it must use radian. So you can put a star there and red pen that is radians. Cannot use degree for the entire of this chapter. Okay? Easier. Okay, so this is the true angular separation. Now, they tell us that we have an 85mm telescope. So let's calculate the theta minimum from the criterion. So that one is sine theta equals to lambda over A. But because I know that the angle is actually going to be very, very small, I'm going to say it's approximately just theta minimum. And then this one must again be in radians. Okay, so the wavelength over A, right? The wavelength is given as 500 nanometers light. So that's roughly green light divided by 85 millimeters. It's 5.9 times 10 to the power minus 6 radian. So okay, really not bad. It's really quite small, right? So my small angle approximation is allowed. Okay, it's microradian. So the question is this number larger or the angular separation larger? It is the angular separation that is actually larger, right? Now, do I want the angular separation to be larger? Yes, right, because the further away apart, the more likely I'm able to see them as two different objects. So, since angular separation is larger than the minimum required angle, the objects are resolved. So this is how we apply radius specular to real life case. So we need two things, angular separation and minimum angle required. Oh no, does anyone have a power bank? Does anyone have a power bank? I'm having less than 10%. Okay, any questions for this? All good? Yeah.
Does it work if you use tangent inverse for the angle?
But I don't need to use tangent and sine, you know why? Because the angles are very, very small. Tangent theta approximately sine theta, approximately theta when the angle is very small. And this angle is ridiculously small, it's like micro-radian. It's not even 1 radian, it is micro-radian.
But tangent inverse formula, instead of using the S over R thing, can you use like 12 over 3?
Yeah, you realize you get no difference. The numbers are approximately the same. It is so ridiculously small because this is like, yeah, it's 73 micro-radian, so it's that small also. Okay.
Radius is in radian.
Yeah, all the calculations must be in radian. It is resolved. Okay. Now, the second column there is the angular separation. So which value am I supposed to choose? This value or this value? This is the angular separation. So I look at a real object and check what's the angle of separation of the real object, right? So this is the answer. So the correct option is resolve and B, B. Okay. You only have the what? Oh, the actual charger. Hello. Hi. Sorry, we're low bat, so make do, okay? Got charger? Who got charger? Come guys, don't let the video die. You know what? Never mind. Someone else